n goes to infinity limit. So now coming back to, let us go further and then see here. So thus one can write the coefficient functions in terms of the Mellin variable. Forget about this resummation and all those things. Let us take a simple fixed order calculation. And in the fixed order calculation, yesterday we have seen there will be terms like what we call as the soft virtual contributions, threshold corrections or threshold terms, and beyond threshold what we call as the regular terms. Suppose if I take only the threshold terms include the curly D plus distributions as well as the delta 1 minus z, Dirac delta 1 minus z type of terms. Suppose if I take those threshold corrections, okay, and look at them in the n space, the same n space. So going from z space to n space does not change the physics. Okay, but at the end of the day, you integrate over z, or if I go equivalently in the Mellin space, I have to integrate over the n. I can always get the physical observable in the Mellin space, but at the end of the day, z is the integration variable that will be completely integrated out. Similarly, in the Mellin space, n has to be completely integrated out. Even for the fixed order case, I can express the entire fixed order corrections in the n space. So again, if you remember, this is the deltas. The way we have defined is just Parton coefficient functions. In the sense, you take the Parton level cross section divided by the sigma naught leading order. So whatever is left over is the Parton level coefficient functions. So then it begins the lowest order. Okay, in the Parton coefficient functions is the delta 1 minus z. In the Mellin space, it begins from 1. So 1 plus the first order corrections alpha s. Okay, alpha s. Now in the Mellin space, it looks like a log square n bar and a log n bar and some constant type of terms. So the coefficients, I am simply calling it as, this is coming at the first order. So I am calling it as a a1i, where I is the power of the log n. So if it is a log square n coefficient, so I simply call it as a a12. 1 stands for the power of the alpha s and 2 stands for the power of the logarithm. And similarly, log n bar coefficient, this is like a a11, and this is a constant term, there is no log n term, so here it is a a10. So a10. Similarly, if I take the second order correction alpha s square, so it looks like the highest power is the curly d3 is there, that is present. If I go to the Mellin space, it looks like a log power 4 n bar and with some coefficient. Again, the same convention I am following. So the a2, the 2 stands for the power of the alpha s and 4 stands for the the power of the logarithm. So it's basically like a aij structure. I is the power of the alpha s and j is the power of the logarithm. So right now, what are these coefficients? Once you do a particular calculation for a given process, you can fix them by explicitly, by comparing the known results, you can fix this, what are the unknown coefficients. So right now, for me, these are, just some quantities which are perturbatively calculable things. So once these perturbatively calculable quantities are there, so now you only look at this, structures. For example, if you see in the alpha s level, we don't have the, log n bar, because at the alpha s level, if you look at it, okay, so meaning at an NLO level, so you have only the curly D1 type of distribution is there. Curly D1 type of distribution which has only the log n square. But you also have the curly D0, but technically if you look at it, so the log n bar, the coefficient will be scale dependent term, and for the central scale choice it disappears. So those explicit, process specific details, I am not going there. In certain cases, if one of the coefficients of some logarithm becomes 0, okay, let it be 0, otherwise it is a non-zero. That is the message I wanted to say. Similarly, if I go to the alpha s cube level, I have the highest power is log power 6. And the next one is a log power 5 and so on. And the series goes all the way up to a30. And you remember, this is a place, in the Parton level cross-section coefficient functions. So there are regular terms. Regular terms also, if you take the Mellin transformations, okay. So then the Mellin transform, for example, if you see here, yesterday I said, the Mellin regular terms can be simple polynomials. Okay, so you can take the simple polynomials, you can take say z or z square, some such type of terms, and you do the Mellin inversion, and then you may get some type of terms like, that go like a 1 by n square, all these kind of terms will come into the picture. So all those things, beyond threshold corrections, they go like a 1 by n, and in the threshold limit, simply because the way we define n goes to infinity limit corresponds to the threshold limit. All these 1 by n type of terms, they will not contribute. So that is how we are ignoring. At least in the threshold region, I can expand the pattern threshold corrections simply in this way. And beyond threshold corrections, they are there, but we are considering only the SV part, the soft virtual corrections only we are considering. Plus, you can say the regular terms, delta regular will be there. So in the n space, all of them look like 1 by n type of terms. So now if you see carefully, what is observed is that at each order in the perturbation series, meaning at each of the order alpha s square, alpha s cube, there is a one dominant logarithm involving the n. Now we are not defining the logarithm in the z space. Everything is defined in the Mellin space. So there is a dominant logarithm at each order, say nth order, of the kind where logarithm power is 2n. If we are looking at the nth order in the perturbation series, so the highest power is 2n bar, and followed by the next dominant logarithm, which is of the order like a log power 2n minus 1. So, and if you go back these things, okay, now if I say now from where these logarithms are coming, it is very difficult whether they are coming from the alpha s or from alpha s square or from curly d3. Those are only decided by the Mellin transformations. So just by looking at some particular say at alpha s cube level, if I talk about the log square n bar, from where it has come, it is very difficult. So it may be coming from curly d5, it may be coming from it may be coming from curly d5, curly d4, curly d3. Various contributions will be contributing to the log square n bar. So all such contributions, I put them together, and the overall coefficient decides the different contributions coming from different curly d's. So instead of summing the large tower of logarithms in the z space, if we go to the Mellin space, we can reorganize the large logarithms, because we have an exact definition of n goes to infinity is a large logarithmic contribution. Again, just to reiterate, this is a very vital point. For example, if you see the curly D3 contribution or curly D2 contribution in the Mellin transformation, you see somewhere it is log cube n bar, somewhere this is this one, okay, and then there is a 1 by n type of terms. Or even if you take the curly D0 type, so there is a some minus sign and some plus sign. You have a variety of contributions, log power 4 n bar, log square n bar, log n bar. Now it is difficult which term is more in nature. So in that sense, we cannot directly say whether curly D1 is larger, curly D3 is larger, curly D2 is larger. But to quantify that thing, it is better directly to go to the Mellin space. So things are much easier, and then you see the higher the power of the logarithm, the higher is the contribution. So now if you see at each order there is a dominant logarithm. So now what about the case where this kind of large logarithm alpha is power n type log of 2n, if it becomes magnitude wise, if it is comparable to the number 1 or of the order of unity, at least of the order of unity, then it means that suppose if this becomes like of the order of unity, now alpha is a square, this exactly looks like the square of this thing. And again, this exactly looks like a multiplying the same quantity. Alpha is a square, log square, log power 4, log power 6. So if one term becomes comparable to of the order of unity, then the second one is also comparable to that thing. So it cannot be, less than this thing. So now there is no guarantee to ignore, or there is no guarantee to truncate the perturbation series, because all of them are equally contributing 1, 1, 1 at each order, at least minimum 1. So now you have to contribute, you have to sum all such contributions to all orders in the perturbation theory. So that summation to all orders in the perturbation theory, if we can systematically organize, by that I mean, suppose if I consider these green colored underlined ones, where at first order I take the dominant logarithm, second order I take the next, again the dominant logarithm, third order I take the dominant logarithm. So like that at each order, if I take the dominant logarithms and I just include as are the essential ingredients in my final perturbative calculation, so then that kind of things is what I call as a leading log resummation. So leading log in the sense at each order in the perturbation theory, this is a leading log logarithmic contribution in the n space. So the leading log, it looks like, alpha sn, and, which goes with the log of 2n. And what about the next contribution, next, dominant contribution after the leading log? That goes like a log power 2n minus 1. This is what leading, next to leading log resummation. So if you consider all such next to leading logs, for example, at alpha s level, I have the log n bar is the next dominant leading log. And at alpha s square level, after log power 4, log cube is the next dominant log. So similarly at alpha s cube level, after log power 6, the next dominant is log power 5. So all these red
Hello?
colored ones. Hello?
Sir, there is a question. Yeah.
Yes, yes.
Hi. So, my question is that when you write this, so this all these alpha s times the leading logs, they behave like order 1 parameter. I mean,
In
right?
the n goes to infinity limit.
Yeah. Then at that point, this perturbation series will not. I mean, the terms are really not small enough, right? In that limit.
They're not small enough. That is why you cannot truncate the perturbation theory.
Okay. Yeah.
That is where we have to consider. So you can truncate the perturbation theory only when you can assume that thing they are small and small enough if you go to higher orders. That is where we have to consider to all orders. You cannot. There is no way that you say that I'm happy. I can alpha is very small. I can stop the perturbation theory.
Okay. Thank you.
That is where we are constrained to all orders. And that is the precise reason when I say leading log, I'm just going all the way from n equal to 1 to infinity.
Yes, sir, I have another question.
Summation is called the, what you call conventionally the summation or the resummation. Yes.
So, for example, in the alpha s limit, you take alpha s times some constant times log square of this. This is the leading log. Now, if we go to alpha s square, I mean alpha s square limit, let's say. So then log to the power 4. But it might be possible that this a coefficient 2 by 4, this coefficient is small. Is it?
Yes.
Is it possible? In that case, like the next two leading order, I mean, in alpha square limit, the leading log is not that dominant compared to the alpha is limit. Whatever.
Yeah, you are exactly right. Okay, but right now, these horizons, if you look at it, I'll just come in a moment. Okay, at least for the leading log, all these things have the same structure. For example, if it has a a12 has a some sort of what we call maybe some sort of cusp anomalous dimension. Okay, so say capital A1, the A24 is related to the same number which is there at the A12 level, which is not a different, completely independent number. But if you go to the sub-leading logs, like a A22, A21, okay, this is, you cannot predict it actually. It has the information of some sort of process-dependent information. I hope I am able to convey these things. So, for example, A12 has some number. You have calculated the alpha S corrections at the NLO level, and you have fixed what is the coefficient of this thing. And this number A12 is directly related to the A24. It is not some independent number.
Okay.
In that sense, it is not only that thing, at least for the leading log level, the highest dominant level, I can also have a predictive power to see what is, if I know A12, I can predict what is A24 and I can predict A36. And that is how it goes, that thing. But if you go to the sub-leading logs, this kind of predictive power decreases, and to improve the predictive power, you have to take some process-dependent contribution. Whereas this A12 I can completely make in terms of the universal number. Okay. So now your question is that whether A24 is smaller than A12. In the sense now A24 is related to A12 only. So it is not a new number completely.
Okay.
Okay. Yeah.
Okay. Thank you.
Okay. So shall I continue further?
Yes, sir. Yes, sir.
Okay.
Oh, there is. Okay. Okay, you can proceed, sir.
Okay, fine. So now here the main point is that thing. So I said that thing. If you consider at each order the dominant logarithms. But how do I consider this at each order only the dominant logarithms? If you look at the perturbation series, okay, so I have, at alpha s level, I have the dominant logarithm in the z space is curly d1. And at alpha s cube level, I have the curly d3. So how do I know exactly, the dominant logarithm at a highest logarithm is straightforward. It's very easy to identify. But the, next dominant logarithms, it is a little tricky. There is a mixture of all these things. For example, curly D3 has a log square n contribution. Or curly D3 also has, this log square n is there, but curly D1 also has a log square n type of contribution. So for example, at alpha s square level, you may have a curly D3 contribution. You also may have a curly D1 contribution. You will have both contributions. Then log square n bar comes from both the places. So this is a little tricky thing. So, but if you want to systematically sum only the, a particular power of logarithms in the n space, then it is better to rewrite how to identify this, which tower I have to take. So that one is, comes, from years of effort, and that is simply encoded in a formula, what we call as a resummation formula. And right now I'm just giving some sort of, a basic sketch of that thing. So there is a systematic way of arranging these logarithms by writing them in an exponential form. So whatever you have seen the, to all orders, basically, if you look at the same thing, okay, soft plus virtual, but to all the orders in the perturbation theory. So this is what if I consider to all orders in the perturbation theory. So effectively I'm considering summing over all such large logarithms. I'm summing over the next dominant logarithms. So that summation is already implicit. So that formula, what I call as a resummation formula, that I can write it as a simply, some, process dependent term times exponential of gn. Now let us go just simple formula. And if you see in the our AMPS poster, somewhere you might have seen some exponential term, and this is exactly connected to that thing. There is no completely different thing. It is exactly that famous Sudoku exponentiation term. And derivation is something different. I can give you some references for this. And right now we will understand how this exponentiation is connected to that summation. So let us consider what is this Gn looks like. So for example, now this Gn, the structure wise, it depends on the type of the process you are considering. For example, yesterday we were we are just highlighting two different processes, namely the De Leon production in the quark annihilation channel and the Higgs production in the gluon fusion channel. If you look at it technically, both come under the same category as long as the Sudoku resummation is considered, because both are having a two colored particles in the initial state. But if you can consider a process something like a E plus E minus goes to QQ bar, there the situation is exactly opposite, in the sense you have the colored particles in the final state, but in the initial state you do not have colored particles. If that is the case, this Gn will have a different form. Or you can take some mixture of these two things, one initial state and one final state. There is a particle, one particle in the initial state, colored particle, and there is a one colored particle in the final state, like in the case of the deep inelastic scattering case. Then the Gn form, the structure will be different. But overall, in all the cases, the G0 times exponential Gn will be always the same. The basic structure, the formula A will be always the same. So for now, let us keep this formula A as the important thing for the rest of our discussion. So for De Leon process, okay, the answer, the expression for this looks like this thing. From where this Gn has come up, just by taking the Mellin transformation of these things, and you have a factor 2, and then this Mellin transformation formula, and what you are taking the Mellin transformation. That is, obtained by, this famous, term, what we call as a Sudoku radiative factor. Okay, very famous thing. And then plus the Gn also has an additional contribution involving the Mellin transformation of another class of, contributions, which like A of alpha s in the first term. In the second term, we have the D of alpha s. What are these A of alpha s and D of alpha s? These are all again perturbatively calculable quantities. So A of alpha s, I can simply expand it like in series is in the perturbation theory. So like alpha s times some unknown constant plus alpha s squared times some unknown constant, alpha s cubed times A3. So I just please hold for 2-3 minutes. You may have some physical picture, some sort of diagrammatic picture. Then you can better understand, what is that it means actually. And then similarly, this D quantities, the functions D of alpha s, are also perturbatively calculable quantities. So I can expand them as a series in alpha s. So alpha s times some coefficient d1, alpha s square times some coefficient d2 plus and so on. So these AIs are the cusp anomalous dimensions. Technically, if they are connected to the cusp anomalous dimensions, the whole idea is that you take the Mellin transformation of these things and then you calculate what is the GN. Okay, assuming you don't know what are the A1, A2, A3, and similarly you assume you don't know what are the quantities D1, D2, etc. And these things, okay, you put them naively in this expression and make the Mellin transformation, and whatever the result you get for Gn, you put it in the exponential and just expand it because now each of the quantities are terms in alpha s. So when you expand it, so you have a terms having some terms proportional to alpha s, and some terms proportional to alpha s square, some terms proportional to alpha s cube. And now look at only the logarithmic structure. Because of this Mellin transformation at alpha s level, you will have exactly the same kind of structure that you have seen here. Meaning whatever the structure which we have seen in the perturbation theory, there is a way, by considering this sort of exponential form, and I can again get back to the same structure. Now, if you know in the perturbation theory, what are these unknown constants? Okay, and by expanding this Sudoku resummation, this exponential resummation formula, and now in this resummation formula, all your answers are given in terms of the A1, A2, A3. So you can fix now the unknown quantities A1, A2, A3, D1, D2, D3, etc. from the known perturbatively calculated quantities. So later, people have realized this thing that all these A1, A2, A3, these are connected to the cusp anomalous dimensions. And what is the meaning of cusp? So that is what we'll just have a look at it. So the first term, what is meant by the first term? In the Gn, this is the first term. Okay, there are two terms in the expression for Gn, both involving the Mellin transformation, z power n minus 1, z power n minus 1. So this is the first term I'm talking about, and this is the second term. So the first term involving the terms A, what do they give information? The first term gives the information about the collinear soft gluon radiation coming from an initial state pattern. Okay, so please note this thing. This is neither soft nor collinear. It is a soft gluon, but in the collinear limit. Okay, so this is a collinear soft gluon radiation of an initial state. So in the sense, you are essentially considering what you call some sort of iconal lines. Iconal line means a colored particle emitting a soft gauge bosons, meaning soft gluons or soft photons. So in that thing, if you consider a special case, they are also collinear to the emitting particle. So if that is the case, the angle between the emitted particle and the emitting particle, so this becomes 0. That is, they are collinear to each other. So that is what the kind of region that we call some sort of cusp. So diagrammatically speaking, this is how it looks like. So imagine this is whatever the some thick line, okay, is going into some hard interaction. Say in the Drellian process, a quark is coming and undergoing into the hard interaction where it interacts with a anti-quark and produces off-shell Z boson or off-shell photon. And before it undergoes, that hard interaction is represented by this some thick dot. And before it interacts, it's just a pure quantum effect. It can emit photons or gluons. So in the QCD, we are just considering only the emission of the gluons. Now, if these gluons are in the soft limit, also if they are in the collinear limit, that is where the entire dominant large logarithms come into the picture. That is the precise region where the most of the incoming energy is just carried away by the this particular Wilson line. So that is just undergoing the hard interaction. So whatever is the energy that is left for the real radiation is very, very small. So in that sense, most of the energy is carried away by the quark itself. So that is the z goes to 1 limit. Similarly, you can consider the anti-quark coming from the other hadron that is also having a, this kind of, n number of soft and collinear gluon emissions. So in that case, what happens is that thing, so most of this quark and anti-quark, whatever the initial energy they have, they carry all the way until the hard interaction happens. So from the hard interaction, you'll produce a final state system like a anti-lepton pair or photon pair, whatever is that one. So the most of the final initial energy is carried away by the final state system. So in that sense, they correspond to exactly what we call as a Z goes to 1 limit, or the fraction of the energy 1 minus Z goes to 0. So this is a special case where energy is not only equal to 0, but the emitted gluons, they are also becoming collinear to 0. Then what about the second term? The second term is this one. So the second term is precisely this one. The second term gives information about the large angle soft gluons. So they are, still soft gluons, but, the angle is not collinear. They are, large angle. So that is why in the, when you see, a particle, a gluon or photon, when it is emitted from a fermion, and in the limit whether the the gluon is soft or collinear, the propagator after the particle, gluon has emitted, it tries to become on shell, meaning there is some sort of singularity develops. So if that is the case, now it has a double such effect. The emitted gluon can be both soft as well as the collinear. The enhancement, the exact singularities will be taken care of by adding with the, loop contributions, the singularities coming from the loop corrections. But the way the energy of the gluon is tending to 0 slowly develops a logarithm, and that is what is manifested as a log n bar that you are seeing actually. And as a result of, two such, enhancements, one is soft enhancement, other is collinear, there is a double effect, log square n type of thing is there. Even if one single gluon becomes both soft and collinear, you'll have a kind of contribution like a log square n bar. Whereas if it just becomes, a soft angle, that's it, then you have the log n bar type of contribution. So in the literature, maybe my understanding is that thing, maybe the cusp anomalous dimension, the way people have done is that thing, you consider first all the soft gluons only. You do not separate them like a soft and hard. Consider all the soft gluons, and then rather you separate them, whether they're small angle, they're in the cusp region, or they're, wide angle, non-cusp region. So accordingly, you can consider. So you can picturize it in a different way, in the sense you can consider first, collinear gluons and non-collinear gluons. Within the collinear gluons, how many are soft and, how many are hard. And within the non-collinear, how many are soft and how many hard. That is the one way of picturization. Another way is that you first consider only the soft gluons everywhere. Then you just define whether they are in the collinear region or they are not in the non-collinear region. Now, if they are soft gluons, by definition, if you begin, that is where the soft gluon resummation, that is the another name for the threshold resummation in the literature. So you consider only the soft gluons. Now you consider the theta goes to 0 limit and theta goes to non-zero limit. So in both cases, you have a different type of contributions. So this the first term that you have seen in the GN is one that has information about soft and collinear gluons, whereas the second term has information about only the wide angle soft gluons or the large angle soft gluons. So here it is a more important because I just showed some formula and I gave a physical picture, but it needs a systematic derivation. I cannot just, hand waving arguments. I cannot put some term, okay, there is a series which looks like exponential, and I also added, I have taken some function like a e power x and I just make a matching. This is some sort of reverse engineering which you can always do, but there is a systematic way of, obtaining the formula A itself. How the exponentiation can happen. So for these two things, if anybody is interested in, I strongly suggest, to go through these works. And if the primary works are important, way back, the original works are given in by George Steinman way back in 87, and by Catani and Frentedouye way back in 1989. I mean, they're fundamental papers, but if you want to, simply understand the concept, to be more familiar, you want to have a simpler, better understanding, not more of the formal aspects, and some sort of intuitive or better understanding. I suggest you take some of the recent papers that came close to 2000. So that is papers by Katani et al. In 2003. This is the same paper from which I have taken this resummation Mellin transformation formula. That is in 2003, and then there is a series of papers, and that also followed later its applications by Ravindran. So the two important papers is on pseudo resummation and on the higher order effects. Then there is also another paper by Mock and others that came in 2005. So it's just for if you want to have a more detailed way of obtaining the derivation. For derivation, I particularly insist for this both 1 and 2 papers more and more important actually. But if you want to see some sort of phenomenological aspects, you can see this the third reference. That is very much useful for you. So let us continue for the next further. So one can write Gn in a more systematic manner. Right now, what all that I have said is that thing. This I can write this expansion formula for Gn. So and now this Gn, if you put it in the exponential and if you expand it, I will get back all those perturbatively calculable large logarithmic corrections. But how do I know that if I want to do only leading log resummation, meaning I want to consider only that tower of the large logarithms at each order in the perturbation theory, only the dominant logarithms at each order. So then the second question comes, if I want to consider only the next to the dominant logarithms, what we call as the NLL. Only if I want to consider that tower, which term of Gn I have to take? And then if I ask another question, so after next to dominant logarithms, if I want to consider the third tower of logarithms, what term in the Gn I have to consider? Right now it is not clear from the expressions I have given. So the Gn, if you take the Mellin transformation, so you can slightly arrange this thing in a different formula. That is, you can expand this Gn after taking the Mellin transformation, particularly after doing the integrations over a and d functions, and take the Mellin transformation and rearrange the terms in a nice manner like this thing, which is a very, very important thing. And this is the exponent you can see in several papers in the resummation everywhere. The same structure is present. Now, why this structure is important? This is important because in the exponential of Gn, if I take only the first term in the
Hello?
exponent. Hello.
Kumar, there is question.
Yes.
Sir, in the expressions of Gn, the first term has a factor 2 and the second term does not have a factor.
Okay, sorry. Very good. I forgot to mention this thing. Okay. So this is a very important thing actually here. This factor 2, from where it comes? Maybe I should explain this thing I highlighted, but yeah. Just let me reiterate this thing. So I mentioned 3 different type of classes of processes, where in the collider experiments, particularly keeping them in mind, you may have both, in the initial states, both the particles are collider particles, like de Leon or Higgs boson production, where QQ bar in the initial state or gluon fusion in the initial state. Or you can have the DIS type of process, where one colored particle in the initial state, one colored particle in the final state. Or you can have E plus E minus goes to QQ bar, where both the colored particles are there in the final state. Now in this particular case, for de Leon-like process, you have colored particles coming from the initial state actually. Okay, in the sense you have quark line and you have the anti-quark line. So both the lines will contribute to this factor 2. And historically, if you see this thing, okay, the iconal line approximations, etc. So the soft gluon part you can always do at the amplitude level, whereas the collinear part comes only at the amplitude square level. Okay, there is a little difference between these two, you have to understand. So in the sense, at the soft gluon level, if there are n number of diagrams that contribute at the amplitude level, I can sum all such contributions and then take the square. Whereas when it comes to the collinear limit, you take that particular diagram which is collinear and square it, and if you have another diagram, you take in the collinear limit and square that one. So you add them at the squared level. Okay, so some of the basic any NLO calculations, you can see this kind of techniques are available. So as a result, if you see this radiative factor, this includes both the collinear configurations as well. So you contribute quark line separately and anti-quark line separately, and then you add both the contributions. That is the factor 2 is coming. But if I take the deep inelastic scattering type of contributions, then you will not keep the factor 2. You just keep only one factor. I mean, instead of 2, you keep the factor 1. But you add one more contribution, okay, where the integration limits are slightly different, and that term takes into account the contribution of the soft and collinear gluons that are emitted from the final state quark line. In the deep inelastic scattering, you have a quark line in the initial state, you have a quark line in the final state. So you have one term for the soft collinear gluons emitted from the incoming quark line, which exactly looks like this entire term without factor 2. And there is a one term which has a information about the soft collinear gluons emitted from the final state quark line. So there, the lower limit will be different slightly. So instead of mu f square, you have the kinematic dependence. It comes like a 1 minus z q square. And if you have the completely, another type of process, E minus E plus goes to Q cube R, then the soft collinear gluons are emitted from both the, quarks in the final state. Then you have the same factor 2, but the limits will be different. So there is one radiative factor for the initial state colored particles. I mean, if the emitter is in the initial state, there is a one radiative factor. If the emitter is in the final state, there is another radiative factor. The difference between these two radiative factors is just the integration limits. That is the message. I hope it is clear. Whereas when it comes to the soft gluons, the way I said, soft gluons can be considered at the amplitude level. So it does not matter whether it is at the quark level or at the anti-quark level. I can consider all their effects in one go and take the square. So you don't add multiple times this kind of contributions. I hope that answers why this factor 2 is here, why not here.
Yes, sir.
Yes.
We can go ahead. Yeah.
Yeah. Okay. So here, I mean, I think it's already 10:30. I just take 10 more minutes. I hope I will try to finish 10 minutes at least I need. So the way where we are discussing is that thing, how to organize the tower of large logarithms in a systematic manner, such that by just looking at the expression of Gn, okay, I know if I take this term, I'm touching the first dominant logarithms. If I take one more term, I'm touching the second dominant logarithms. So if I write Gn in this particular form, the same thing, whatever you have seen the integrals involving the first term having the a functions and the second term having the d functions. So if I integrate and then do the Mellin transformation, then I organize in this particular fashion, and then you take only the first term in the exponential and turn off all other terms and just expand the exponential. Okay, so then you will see exactly only the dominant tower of logarithms at each order in the perturbation theory. Whatever you have seen in the perturbation series at alpha s level, you have log square n. At alpha s square level, you have log power 4n. So those exactly only those terms will come into the picture. So and then if I include first term as well as the second term, then I can include both the first tower as well as the second tower of the logarithms. This is what we call as the NLL resummation. If I include the first three terms, then it
Sir?
is clear. Yes.
Can you please repeat from the previous Gn expression how you are landing up with this Gn in term of n, because there the integration is around z to the power n minus 1 by minus 1, so it's not exactly the Mellin transformation, right?
No, this is z power n minus 1. If you see, this is the Mellin transformation, but because you have the curly D type of nature, which is sort of plus distribution. Basically, the plus distribution or this A's, the cusp anomalous dimensions, both are identical in nature. Okay, so because of that particular plus distribution, you have an additional minus 1 behavior actually.
Okay.
That is what you see in both the cases. If you take only z power n minus 1, that is the simplest thing. Whatever you have seen, this is the Mellin transformation. Okay, and these are not just it is not simple log of 1 minus z you are taking. It's acting on a plus distribution. Plus distribution, the way we defined yesterday, something also has to be subtracted eventually. So that takes into account in terms of this -1.
Okay, thank you.
Okay. So now again come back to this thing. So I hope now it is understandable, right? So you first here in the first time you do the Q integration, and after doing the Q integration you take this 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 Z integration. Okay, that is essentially sort of it is a Mellin transformation. Okay, so now if I after doing both integrations with respect to Q square as well as Z for the A functions and for the D functions, you do the Z integration, then you organize the the resulting logarithms in this particular order. Then you can clearly say that if I take only the first term, I'm taking only the leading logarithms. That you can, the entire idea of organizing in this particular fashion is just to obtain the leading logarithms. If you organize in a different way, maybe you randomly picking up logarithms at a different orders, different powers. But if I organize in this way, it is ensured. If you want to check, the only thing is that you just put the gn in the exponential and just expand in terms of alpha s. So what is this g1? I'm just giving an example of g1. So g1 is nothing but a1 by beta naught into 2 minus 2 into log of 1 minus lambda plus 2 log of 1 minus lambda
Hello.
into lambda inverse.
So,
Yes.
sir, in this Gn expression, why this G1 only have log n, not anything else like G2, G3?
Only g1.
In the expression, if you see above, capital Gn,
Oh,
they
this log in bar, why it is there?
are.
No, that's what I'm saying. This is just, that is how we have written, so that if I put back in my exponential and if I expand it, I will only get the dominant logarithms. If I take only first this term, suppose if I put log n bar to this one, okay, and you expand it, well, you will get a different tower of logarithms. But this different tower of logarithms will not correspond to your dominant logarithms. Then the organization is a little non-trivial for you.
Okay. Okay. Thank you.
Yeah. So then I'm just giving an example of what are these coefficients g1, g2, g3, g4. These are what we call as the resummation coefficients. Each of them are functions of lambda, where lambda is simply given to you by 2 beta naught as times log n bar. Okay, so here now if you look at the expression for this g1, so this is just one example, and if you go to the expressions for g2 and g3, which the references I have shown you before, either in the Katani's paper or in the Mook's paper or Ravindran's papers, you can see all these expressions for g1, g2, g3. Maybe the terminology may be slightly different. You can see somewhere like instead of g they may be using the word c0, but the physics is the same. And they have this kind of structure. Essentially you have the log of 1 minus lambda, where lambda is contribution of something like this. Now the interesting part is that thing here, n is eventually a Mellin variable, and if you want to go to the your physical observable, you have to integrate over the n. So n as such is not a constant number. It's not a fixed number. Z goes to one limit corresponds to n goes to infinity, and you are integrating in the z space, you are integrating z from 0 to 1, and in the n space you are integrating from minus infinity to plus infinity. So if you do that thing, okay, there is a region where in spite of this beta naught small number and as is g alpha s by 4 pi, alpha s is gs square by 4 pi. The as is even much smaller, but you will always find because n is a variable number, you will always find some region where this entire value becomes of the order of unity. That is lambda can be equal to 1. So then there is a different problem that G1 itself, explodes. It's like big number, and this big number you are putting in the exponential, it will create a chaos. Okay, so that is what we call as historically, simply speaking, this is a there is a singularity, and this singularity is of a different origin, and that's what we call as a Landau pole actually. So now how do we do the integration over n? Obviously, when you are going from minus infinity to plus infinity, basically you are taking all values of n. Somewhere, you will hit, corresponding to this value, lambda can be unity, and this pole you will not miss. That pole will be there. And same expressions if you see for G2 and G3, which are there in the other terms, G2 and G3, you will have, similar log of 1 minus delta. This pieces will be hanging around. So, which essentially means that pole you cannot avoid it. But how do I do the integration with the presence of this pole? And this is some special pole, unlike, other type of simple poles, like a 1 by n plus 1, 1 by n minus 1. Okay, where you have, this kind of poles, 1 by n plus 2, for example, if you take. Suppose in the entire, if I include the regular terms also in the calculation, in the perturbative coefficients, then, if I take the Mellin transformation, then you will see some terms like a 1 by n plus 1, 1 by n plus 2. Then when I'm taking the integration over n from minus infinity to plus infinity, so you may be having a pole at n equal to minus 2. You may be having a pole at n equal to plus 1. So these are all, what we call as a simple poles. And when you go to the complex plane, you choose a contour in such a way that, all these things will turn out to be some sort of residues. So these are not a problematic thing. But there are, only when for large value of n. Okay, so some value of n, when n is becoming very large, it will hit the Landau pole, and that is a sort of, there's some physical connection. Even if you are doing this, evaluation of the coupling constraints, you will see this kind of problems are there, in the RG evaluation of the QED coupling. You will see sometimes, the beta functions, some of the coefficients, you have 1 by 1 minus the coupling constant times some terms involving the scales. When one of the scale log of q square by mu square, when one of the q square becomes very large, then the entire denominator becomes 0. So they have some sort of serious problems. Physically that is in the RG evaluation that is a different context, but in this present context you have to avoid while doing the n integration. So that is where we follow something called, a prescription called the Mellin minimal prescription to avoid this thing. So let us once again quickly recall. The idea is that the resummation formula, whatever the A formula that you have seen before, okay, can be used to account for the large logarithm systematically to all orders. And what about this G0? I never touched it so far. I only insisted on the Gn. The G0 is a term which has information about all the process dependent contributions. And again, let us recall this Gn. If you see a sort of diagrammatic approach, you can see before it goes into the hard interaction, it all happens at the external level, okay, external lines. Okay, so in that sense, this part can be truncated from the hard interaction process. So in that sense, these are like a sort of process independent, and they can be exponentiated. And what about this Z0 that is sitting? So that has, G0 means it is independent of n. It does not have any dependence on n. That is why it has been pulled out. Now, what are those terms which are independent of n? If you go back to the Z space contributions, only the delta 1 minus Z type of contributions, when you make the Mellin transformation, they become independent of n. They're like a constant in the n space. Okay, they do not have any n dependence. So now you look back and see from what are the configurations where you will get delta 1 minus Z. The process dependent delta 1 minus Z at higher orders comes simply when you do the loop calculations. All the technology that you are learning so far, maybe in a different techniques, in different techniques in the sense starting from the generation of the diagrams and all the way going to the reduction process, and then finally end up at the master integrals. And if you are stuck up in solving the master integrals, how do you design different methods to solve the master integrals, and finally you get a finite answer. And that finite answer corresponding to a given loop diagram is what is going inside this Z0. This is also a perturbatively calculable quantity, and which you can expand in terms of the alpha s or AS, which I can say for the Delian-like process, say 1 plus AS Z01 and the AS square coefficient Z02, etc. So which means that the G01 coefficient at NLO level has information about all the one loop, all the delta 1 minus Z contributions at the one loop level. It may be more than that. The best way of obtaining what is the Z0, or what is the best way of obtaining G01, You cannot take one diagram, you cannot take one process. The best way is that thing, you take the entire NLO cross section, NLO pattern level cross section coefficient functions at the NLO level. You take the entire, coefficient functions at the alpha S level, you make the Mellin transformation of them. And after taking the Mellin transformation, you look for those terms which are independent of n and put them inside the G01. That is the best way of doing. If there is a loop contribution coming, it will be included. It will be included here. If there is a certain soft limit, okay, the function also gives some delta 1 minus z limit. That also will be included here. So it does not matter from where all these delta 1 minus z pieces are coming. Okay, so at the end of the day, you will get it. Not only this, delta 1 minus z pieces. Even if I take the curly D Mellin transformation, okay, there will be some terms independent of n. So those things are also independent of n. So they also will be kept inside the Z0. So all those terms will be systematically included. This is a separate work as such. How do you extract the Z0 or the process dependent information? For that, you just take the full fixed order result at a given order and make the Mellin transformation of the full fixed order results and extract only the n independent pieces. And that's what you put them at the one loop level, call it as a Z01, at the two loop level, call it as a Z02. So alternatively, the formula A can also be used to expand the results. So in other words, you just take, because Gn eventually it is written in terms of the functions A and D, and G0 is also expanded in terms of AS, in terms of the series expansion alpha S. So eventually, if you expand this entire Z0 times this entire exponential Gn, alternatively you can expand this entire formula, okay, and obtain the threshold corrections at any given order. Okay, suppose if you expand this entire formula, you will again take, you will have the terms like a alpha s power 0, alpha s power 1, alpha s power 2. And at each order, if you want to have the NLO threshold corrections, look at only the alpha s power coefficients and ignore all other terms. Okay. If you want to take up to the two loop level result, you keep the up to alpha s power 0, alpha s power 1 and alpha s square level and ignore the higher powers in alpha s. That is how you can just use the same formula and expand it to get the, whatever the known threshold results that we have in the n space. So for nth order, the threshold result, we need terms up to G0n. I mean, this is obviously understandable. Suppose if you want to have the full nth order result, you also need to have the Z0. So this is where historically, there is one point I like to highlight it. This is a place, this Gn is some sort of universal quantity. So I can do as such, in the Gn, if you look at it, I can take 1, 2, 3, 4 terms, I can do it. Imagine for a process where, these are all sort of universal quantities, I can consider all the 4 terms in the exponential, but outside the exponential, I don't know even the 2 loop level result. So in the sense, I'm not even aware with the G02. Well, then I can put Z01 up to Z01, but in the exponential, I can take up to the 4 terms. And now this is different way. You are calling this as, if you take 4 terms in the exponential, you call this as the N4LL resummation. But when you are matching to the fixed order results, you don't have the fixed order results even at the 2 loop level. So you have to systematically match. You have to systematically add to the only available NLO results. So that is a procedure which we just come back in a moment. So Z0n essentially contain the information about all the hard virtual contributions, or essentially all the process dependent information is there. The formula A as such contains or resums the large logarithms to all orders starting from alpha s corrections. So whatever this formula which we are saying, this has information about all higher order pattern level coefficient functions. Okay, so ideally we need to have the complete fixed order results for every alpha s. Okay, if somebody says, I want to improve the precision, what you should have simply, I need to have the complete fixed order results at every order. But practically that is impossible to calculate a complete fixed order results to all orders. So, but because of this universal nature, at least we can calculate, some of the, dominant logarithms even at higher orders. But for the process dependent things, we know only very limited terms. Okay, so then this is the place, where, if I have a series of logarithms which are valid to all orders, but on the other side, the exact fixed order results, I know only a certain order. And when I say this resummation formula A has the information about the logarithms to all orders, which means that it also has the information about, those orders. For example, let me take a simplest example where, where I know the results at n square LO level. Only at n square LO level I have. Say, for example, let us consider a scenario where TT bar production. I don't have in the full exact theory, I don't have the n cube LO result. I have only the exact n square LO available. Let us say as of now. Okay, now is there a way that I can do the resummation so that I can consider the dominant large logarithmic contributions in giving the predictive powers for the quantum level calculations. So then what I have to do is that I have to use this formula, resummation formula, to calculate to include the information about the higher order corrections, higher order logarithmic contributions. But on the other side, I know the existing n square LO results. So I have to add these two things. But remember, the formula A also has information about NLO logarithms and n square LO logarithms already. So if I naively add these things, say for example, if I naively add the known fixed order results and I add the entire formula A, the resummation formula to the known fixed order results available. Okay, so what does it mean? So there is some sort of double counting. Where is the double counting? In the fixed order results, when I say this thing, I know the results up to n square LO, say for TT bar production process, which means that I know the full alpha S corrections, and then I know the full alpha S square corrections, and in the NLO corrections, there are logarithmic contributions are there, and at n square LO also there are logarithmic contributions. But when I add the resummation formula, there also it will only give the soft plus virtual corrections, and in the soft plus virtual corrections in the n space there are again alpha s square alpha s logarithmic enhancements are there, alpha s square logarithmic enhancements are there, but this is a resummation, so it has the logarithmic enhancements to all orders. Now if I add naively these two things, so at alpha s level the logarithmic contributions I am counting them double. So that causes a double counting problem. So I should avoid this thing very carefully. And this sort of avoiding the double counting is called a procedure called the matching procedure. So how do I do that thing? So to avoid this double counting, we need to subtract the logarithms up to alpha s square level. In the present context, I am adding the resummation results to the available n square LO results. The main point is that to what order of the fixed order results that are available. If you are adding to the NLO results, then again you avoid the double counting only at the NLO level. If you have the fixed order results, say for Higgs case, you have the up to n cube LO results, and you want to add the resummation contributions to that thing. So in the resummation, you try to avoid at least up to alpha s cube level the known logarithms. So what type of double counting you avoid is decided by the fixed order contributions that you are adding to. So in this particular present situation, we want to add to the known fixed order n square LO results, say for a given process. So we have to avoid the known up to alpha s square, the threshold corrections. So how do I do that thing? This will do it by expanding this resummation formula A in the n space itself and expand it up to alpha s square level and ignore the higher order terms. And that particular expanded and truncated version is, let me call this as a name called the resummation formula. You expand up to n square level, meaning up to alpha s square level, and truncate it. Technically, if I expand this full resummation formula, how does it look like? So it exactly looks like, again, 1 plus AS, all the alpha S contribution, alpha S level, all the threshold corrections, and at alpha S square level, if I expand it, it has corrections up to all the alpha S square level, and it also has the corrections at alpha S cube level, all the logarithmic enhancements, okay, and at alpha S power 4, and so on, it goes on. But when you expand it, you truncate it up to AS square level, meaning you ignore, other than the red colored ones, ignore the higher order ones. Okay, and this is what the resummation formula expanded and truncated to a given order. To what order you have to truncate it, that depends on, to what fixed order results you are adding the resummation results to. So in this case, simply I'm adding to the n square L of fixed order results. I expand the resummation formula up to alpha s square level, and then I just add I add the matching procedure. How do I do this matching procedure? So this is what exactly it happens. So thus after matching the results we have. So what is the thing? So you take the known fixed order results which has the information up to as square level, and you take the full resummation results which has the results all the way logarithmic contributions all the way from alpha s level to alpha s power n, where n is very large, and then you subtract the known results up to alpha s
Hello,
square level.
sir.
Hello.
Sir,
Yes.
5 more minutes.
Yes. Okay. Very good. So then I just truncate these results. So up to alpha s square level I truncate. So then whatever the result I have is, this particular combination is what is called the matching procedure. So in this matching procedure, what you have is the terms only beyond alpha s square. So from the resummation formula, so I have removed the alpha s square contribution. So this formula acts starting from alpha s cube level. Suppose if I'm adding to the NLO level, what I do is that thing, I just truncate only at NLO level. And so then this matching includes the terms from alpha s square level onwards. Suppose if you are adding to the n cube LO level, you truncate up to n cube LO level, so that this entire combination involves the corrections starting from alpha s power 4. So that is how in the known results, I have the nth order results, and from the resummation, you have the logarithmic enhancement coming from the n plus 1th order. This clever way of doing is a matching procedure. So depending on what order of the results that we know in the fixed order, there are different ways of matching that you see in the literature. And finally, what is the thing? There's only one last concept is, the finally what we can do is a Mellin inversion. So now I have all the results in the n space. So this is what I call the final result. So let me call this as the, sigma n square L of fixed order results, and I have done up to the n square L resummation. So this entire quantity which is available in the n space, I do the Mellin inversion. Mellin inversion is defined by this way. So now I just take where tau is a physical variable, whatever be the space you want to come back. So you want to come to x space or tau space or z space, you take that variable here and then power of that minus n and integrate over that n variable. So this is a Mellin inversion. So while doing this Mellin inversion, what are the problem I said? That Landau pole problem will be there. So that is where we have to avoid it. This is the last slide I'm showing. So that is where we have this kind of situation where if I take simply the minus infinity to plus infinity, where x-axis is the n value. So somewhere you see this kind of the problem of Landau pole, where lambda equal to 1 it becomes. So that is called the Landau pole. So to avoid that problem, what we do is that thing, we treat n as a complex number. So far I never introduced, I just said n as a variable. Now you can treat this as a complex number, and you can, if there are any simple poles like a 1 by n plus 1, 1 by n minus 1, all those simple poles you keep it to the left of the contour, and then you see what is the highest simple pole that you have in the problem. So you define a point C such that all the simple poles are kept towards the left of this contour, and only the Landau pole is kept on the right side of the contour. And then you just close the contour in this way. So this kind of choosing the contour is, we can say, I mean, this is a clever way of, avoiding the Landau pole. And so that in the integration contour, you don't have the Landau pole. Because once you include the Landau pole, there is no way that, whether it will give, any finite answer, whether it is integrable singularity or not, we don't know. So you avoid in the contour region itself this Landau pole. So then what is the choice of the value of C, and what is the value at which you take the contour deformed? So that values are, is given in a paper by Pegasus by Fort et al. So the value of C is chosen to be 1.9 and phi equal to 3 pi by 4. This same choice is also taken in the initial paper by Katani in the Higgs resummation way back in 2003, the same thing. But initially, this thing he will not, the Pegasus, they will not much insist on the land of pole, etc. They will say what is the best efficient way of optimizing the Mellin space PDFs. This is the efficient implementation of the Mellin transformation, Mellin transformed PDFs. They do it in a different context. Now they are also used for doing the Mellin inversion in our present case. So that is the whole point I just like to say. Only thing I could not cover, I did not mention because it takes some time about how you derive the T-summation formula and what is the connection to the factorization theorem, the famous QCD factorization theorem. So of course within these two lectures it is difficult to cover many things. Any of the interested readers, please go through the references I have suggested, and I feel there is a good place to stop this lecture. Thank you very much for your attention.
So, question from the audience.
Sir, I have a very simple doubt. Where you are showing the Katani's formula for the summation in page number 1 or 2, can you show it again?
Mellin transformation formula.
Yeah, this part. So yeah, so here in the second term we can see that zeta 2s are coming, but for D3 and D4, zeta 3, zeta 4, all such things will come. So are this encoded in this A n comma K?
Yeah, A n K. These are all constants.
Okay. And another question is, like, for example, when you consider this D2 or D3, like we can always predict if we have let's say the leading log, all the leading log coefficients, we can predict all, I mean in the entire series of the perturbation we can predict all the coefficient for the other leading log to the power n's, right? So is it true for next to leading log, next to leading logs, and so on?
No, you cannot predict it. Only the large logarithms you can predict, meaning the coefficients of the logarithms, the prediction of the coefficients of the logarithms, right? That's what you are asking.
Yes.
Am I right? Yeah.
Yes.
So the mixture is the following actually. If you see, I mean, sometimes it is very difficult to have a physical picture in terms of the mathematics, but if you have a some sort of physical picture from the diagrammatic approach, suppose you have this kind of a diagram which is undergoing the hard interaction. Suppose imagine after the hard interaction, okay, and imagine there is a loop here. Imagine there is an anti-quark line. I don't know if you can see what are the cursor I'm moving.
Yes.
Suppose there is a quark line and there is an anti-quark line, and imagine there is a loop connecting from the quark line to the anti-quark line. Okay, and after this, loop gluon has been exchanged. Then there is a soft gluon has been emitted.
Yes.
You understand this thing? So
yes.
This kind of thing you cannot fully factor out. But these kind of contributions will enter in the realistic calculations. But where do I see them? In that sense, the information about the one loop corrections also has to come into the picture. Or in other words, suppose you take one soft gluon has been emitted. After that thing, one gluon exchange has taken place between the quark and anti-quark. That kind of things, then the entire thing is not proportional to only the underlying hard interaction, but the entire thing is proportional to the underlying one loop interaction, one loop contribution. So then all those things will be reflected as the coefficients of your log square and subdominant logarithms.
Okay.
How do I include systematically? If I do not include those one loop contribution, then I will be missing some part of the coefficient of the subdominant logarithms. To account for this thing, we added this additional term, this G0.
Yes. Okay.
So now if you miss this thing, you will not fully capture the, other than the dominant logarithms, meaning straightforward. You do not consider any loops or anything. You just consider until the quark line, whatever be this, incoming Wilson line, and entering the hard interaction, you only consider the real corrections, which is straightforward, you can factor out. But the gain is much more non-trivial. Then you have to consider the real gluons emitted in presence of the virtual gluon exchanges. Then in such cases everything is not proportional to the underlying bond, so some terms are proportional to the underlying loop calculations. So then you have to include the lower order process dependent contribution. So those lower order process dependent contribution enter as a quotient of this in the A31 etc. These things you cannot predict it unless you know the lower order contributions. That is the message I want to say.
Okay, any other question? No. So we can stop sharing.
Okay, fine.
Okay, so before we end this session, I want to thank Kumar for taking his time to give 2 lectures. Thank you, Kumar. And
thank you, really.
and as we sort of discussed in the just before the last talk, we expect that you will organize a workshop in your place. Okay, if it is possible.
I will try. Yes, I will try.
It is just a request from our side. If you can organize, because Guwahati is a beautiful place, and also your institute is also very beautiful. So, we'd be happy to come there and have a, discussion meeting, because this is a school. But the next one, as Amresh has always been sort of proposing. We'll have, alternatively workshop, like this, school workshop. That way we can actually sort of have a hands-on sessions and things like that. So, if possible, you can organize a meeting, by end of this year. So, that's a proposal from Amresh and myself. That if you have something like this, then it will continue. This, you will not lose this team. Okay, we'll do that. That's one thing that we wanted to, because it's not just we listen and go. We also wanted to sort of interact. Okay, that's one thing. And I also want to thank Amresh, because I allowed to leave in between for some urgent work. So I want to take this opportunity to thank Amresh. Amresh is the lecturer who is going to stay for the entire period. So I have a special thanks to him, and also a special thanks to him because he is the originator of this entire AMPS, and I think we should continue this sort of having.
I think name is created by him.
Him also. So he started the program, and I think we'll have to take it forward and for next several decades. Okay, because we should have one such, like there are schools and this kind of a intense meeting on a specialist topics in Europe and US, in the name of CTEC or Loops and Legs. RADCORE is more like conference school, some smaller versions actually. In India we should have, because we have a great strength. Most of you are actually, very smart and, energetic. I think we should have one such, every year we should have 2 programs, and in next few years we should expect people from abroad coming here and learning. I think that should be the goal. Okay, so not just increasing the number, but also visibility. So this school should be a, some kind of a trademark for India. Okay, that we have such programs. So because we have a lot of talents. So I think we should continue. So I want to thank everybody who come all the way, because I may not be there in the last session. I have to leave for some urgent work. Okay, so thank you all, and keep in touch. And tomorrow most of you will be around, and we have arranged discussion sessions, and you should actually meet with each other. It's not just meet the speakers. Meet each one of you, and tell what you are doing. This way you can have a cross interaction, collaborations, and so on and so forth. That's how we can develop. If you are just independently doing things in 10 different topics, I think we cannot actually make a big impact. If you join together and learn from each other, and there is a possibility of coming up with some big things. Okay, so collaboration is very important. Okay, it's very important. So as you can see, many of the speakers are my former collaborators. Okay, so that's how it has been developing. So collaborate and in next 10 years, you will be speakers of some younger generation. So I'll stop here with my gyan. Okay. So I want to thank Kumar and Amresh, originator of this program. Let's continue with this same. And also I wanted to before I forget, of course, this program is not run by me. Okay, even though my name is there in that, somewhere, but I contributed 0. Okay, who contributed the most are these two gentlemen who are sitting in the front, and some of his friends, through some possible ways. The friend, the gentlemen are, Saurabh and Vaibhav. Vaibhav actually, created that poster, and Saurabh joined later on to refine. You can see the poster is the kind of talk of the town. Okay, so and after that they independently, without even discussing with me on anything, they ran the show. Okay, I gave no advice, no contributions to this. Everything. If you ask me how many of you have come, I cannot tell the number. So that means this everything goes to them. And also I wanted to thank people behind the scene, like many register, common section, and the media. The person whom you saw, Mrs. Gayatri, and her team. They all worked behind us and then contributed to a lot. The registrar, administrative officer. There are all many people who served food and all. They are also part of it actually. And I wanted to take this opportunity to thank all of them. I wanted to record this also because it's recorded. And there are many people actually, transportation, apart from speakers, there are many. So this is an opportunity for me to thank all of them. And I want to thank you also to come here. I think the number should increase. Next time when we are meeting anywhere else, number should be double. So that's our dream. Okay, do contribute, do well. Happy journey back home. Thanks. Thanks, Kumar.
Okay, fine. Thank you all. Okay, so I'm signing off now.
Please.
Back.
Hello.
Yeah.
Sir, your bag and certificate will be given to your students, so please take it from them.
The certificate.
You'll get
Okay.
certificate also.
Okay. Yeah. Thank you.
Good teacher.
Thank you, sir.
Yeah, where I do actually cover the entire model. But it has basically both the formal as well as numerical aspect, because whatever basically formalism is developed for a spanner model, I try to basically make prediction out of that, so that you know where they go, instead of basically just saying, okay.
Thank you. It's on, right? Should I start? Okay. Okay, so welcome back, and this is the last lecture of this school. After that, you have plenty of time for discussion, and I hope that you will utilize that time as well. So let me recall what we did in the last lecture. We were able to see that how higher point function, okay, in 2 to 2 processes, they can be, the tensor integrals can be reduced into corresponding scalar integrals and lower point scalars. So we have come across tensor integrals corresponding to 2-point functions, tensor integrals corresponding to 3-point function, tensor integral corresponding to 4-point function, and all these basically appeared in our example of e plus e minus to mu plus mu minus at one loop. Okay. So as far as say loop corrections, one loop corrections in this process 2 to 2 process are concerned, we have basically done the job, because we know that higher point tensor integrals, they can be written down into lower point tensor integrals, and eventually you reach a stage where you are left with only scalar integrals with no loop momentum in the numerator. So natural question arises, what happens if I discuss 2 to 3 processes? For example, because of some reason your experimentalist friend would be interested in analyzing data on this process mu plus mu minus and a photon, and then he or she would like you to make a precise prediction for this, and when you go on doing it, you are going to come across a diagram which is like this. So E minus, E plus, mu minus, mu plus, and a photon. Okay, this would be a new type of diagram which would appear in your computation at one loop level. And of course, if you go on actually more and more final state particles, you are going to come across one loop integrals with more number of propagators. So whatever we have learned, we can expect that we would again come across some tensor integrals, for example, say L mu, L nu, L rho. In this case, you will come across with D0, D1, D2, D3 and D4 propagators, okay, because I have got P1, P2, P3 and P4 as the independent momenta, and P5 is fixed by the momentum conservation. So at least we can sort of actually say that the way whatever we did there, we should be able to do exactly the same thing here and reach a stage where I am left with only scalar integrals, and that happens to be true, yes indeed. However, when you are discussing a 2 to 3 process or 2 to 4 process and so on, there is something that you should basically keep in mind, and that is that in 4 dimensions, okay, you can have actually 4 linearly independent momenta. So any momentum you can, any vector you can express as a linear combination of 4 independent momenta. So this P1, P2, P3, P4, they can serve as the basis for expanding the loop momentum. Okay, instead of writing down the most general structure, you can basically avoid that if you notice that in 4 dimension loop momentum should be expressible in terms of P1, P2, P3 and P4. Okay, so this is what actually we will do. And so far whatever we did, we said we will do in d dimensions. D is equal to 4 minus 2 epsilon dimension. However, as we will see that in the case of 5-point functions or tensor integrals with 5 propagators, all the tensor integrals as well as the scalar integral that you come across from the naive power counting, you can see they are all actually ultraviolet finite. Since they are actually ultraviolet finite, you do not actually need to worry about the reduction process being failing somewhere, and we will see how. But that's actually main point. So when you are in actually 4 dimension, this set is sufficient to express your loop momentum, and this we have written earlier. For example, L mu in 4 dimension I can write is equal to 1 to 4 using the notation of the momentum p's and their corresponding dual vectors v1, v2, v3 and v4 in this case. So that is L dot pi vi mu, or you remember the set of q and u, where q was basically sum of q1 is p1, q2 is p1 plus p2, q3 is p1 plus p2 plus p3, and q4 would be p1 plus p2 plus p3 plus p4. I would like to actually work with that, and correspondingly instead of v1, v2, v3, v4, the dual vectors which satisfy the property that qi dot uj should be equal to delta ij. So I can use that depending upon what is more convenient to us. Okay. So these 4 vectors they span the whole space in 4 dimension. So you basically can just rely on this. There is no need to basically explicitly write down the tensor decomposition of this kind of actually integral in terms of say g mu nu and so on. You can do it. Okay. So because of the same reason, now if you recall, for example, when you do the tensor integration, we do come across this g mu nu. But in 4 dimension, because of the fact that you have 4 vectors, g mu nu, you recall, my omega mu nu is now 0, right? And omega mu nu was written in terms of g mu nu and g mu nu hat. Okay. So when omega mu nu is 0 in this case, therefore g mu nu is nothing but g mu nu hat, which, as we had defined, is qi mu ui nu. Okay. So the metric itself you are able to write in terms of the vector and its dual vector. So what it means? It means if suppose that you want to do the decomposition of L mu L nu with this 5 propagators, there is no need to basically put this term. So there will be g mu nu plus other combinations. This is not independent. At the level of c mu nu, at the level of b mu nu, at the level of d mu nu, this was actually independent term. But in 4 dimensions, in 2 to 3 process, because of this fact, this g mu nu is completely expressible in terms of this. Okay. So the decomposition that you do is basically an overcomplete, and this is true for both say second rank tensor and any higher rank tensor wherever actually g mu nu appears. Okay. So this has nothing to do with basically a theory. It's basically based on simply that in any so as I said, basically in 4 dimension, I can have actually maximal 4 linearly independent vectors, and everything else can be expressed in terms of that. It's like basically vectors in 3 dimension, right? I know basically 3 orthogonal linearly independent things, and I express them. Anything, any vector can be expressed as a linear combination of those. Okay. Okay. So this is what I want to do. I want to basically start from here and show you how, in the case of 5-point function, the reduction would proceed. And we will do it in 2 steps. The first step would be to show a higher point to a lower point in the tensor integral, and then the second part would be to show that this scalar integral also can be written down in terms of lower scalar integrals. Okay. So let's do the first part. So my L mu is L dot qi ui. That's what basically L mu I would write in the basis where I use q and u, and L dot qi is written in terms of the propagators. So half di minus d0 minus qi squared. Okay. And since I am in 4 dimension, I am going to use the expression of these vectors in terms of generalized epsilon tensors. You remember I had introduced in the case of P1 and P2, the V1 mu was written as epsilon mu P2 divided by epsilon P1 P2. We had chronicle delta representation, okay, which we started with, but if I am in the integer dimensions, I can actually work with generalized epsilon tensors. So in this case, what do I have? I have actually 4 such vectors, dual vectors ui, which are mu, q2, q3, q4 divided by epsilon q1, q2, q3, q4. So this is u1. Similarly, I would write u2, u3 and u4. Okay. So, for example, U2 would be Q1 mu Q3 Q4, denominator remains same. U3 would be Q1 Q2 mu Q4, denominator remains same, and Q4 would be Q1 Q2 Q3 mu. Okay. Okay. So, with that, my L mu is minus half. First, this I will write this term I Qi squared times Ui mu Okay. So, I think I would like to actually miss a step. Instead of doing this step, I will directly write that result, because you know what do I have to do. The next the step I am going to do it is just for the organizing different steps. But the main point is that I want to now express everything in terms of these quantities, and I already see that what I have to manage di, d0 and qi. That's it. So, this is half. From all the terms I can take this common, q1, q2, q3, q4. This is here. Oh, I cannot do that. So, okay, let me do that step, because there is some new things to be stated. Okay. So, this is your d1, d2 is epsilon q1 mu q3 q4, d3 is epsilon q1 q2 mu q4 plus d4 q1 q2 q3 and mu. Okay. And minus d0. With the d0 I get just this term, which is sum over I of ui mu. Okay. So, I have written down these terms, I have expanded all these, and then I am left with this term here. So, I would write that as well, minus sum over I qi squared ui mu. Okay. I just basically expanded. Now, this is an exercise for you which is not very difficult, and it would allow you also to understand and appreciate this notation. What is that? This is sum of u1 plus u2 plus u3 plus u4, and if you do, the exercise for you is to show that this is v1 mu. And what is the v1 mu? v1 is the dual vector in the space spanned by p1, p2, p3 and p4. So, this is epsilon mu p2, p3, p4. Okay. So, this is an exercise for you. We can do it in the tutorial also. Okay. So, that is one. Second, let us look at actually this term, just this one, epsilon mu q2, q3, q4. Okay. Let us write them explicitly. Epsilon mu q2 is p1 plus p2, q3 is p1 plus p2 plus p3, and q4 is p1 plus p2 plus p3 plus p4. Now, because of the antisymmetric property, although I have contracted indices, what you will find basically terms like epsilon mu p1 plus p2 and again with p1 plus p2 and again, or whenever two of them are actually same, it would be 0. So, what you would have is epsilon mu p1 plus p2, p3 and p4. That is what basically you would have. It works exactly like the contracted indices. So, since I have already got p1 plus p2, therefore, here I cannot have p1 plus p2, here I cannot have p1 plus p2. That is the first step. Second step, here I have p3, so here I cannot have p3, and therefore, this is epsilon mu P1 plus P2, P3 and P4. Is this fine? Now I apply momentum conservation on this P1 plus P2. I can write as minus P3 minus P4 minus P5 because I am taking all the momenta to be incoming. And again apply the property that if, since already I have got P3 and P4, therefore this term cannot have P3 and P4, so only P5 would be left. So this term is minus epsilon mu P5 P3 P4. Do you agree with me? And then I'll use basically the property and put this actually here because it crosses two indices, therefore there will be no change in sign. So that is just minus epsilon mu P3 P4 P5. Negative sign? Negative sign came because I used the momentum conservation P1 plus P2 as minus P3 minus P4 minus P5 because of that. Okay. So what I want to basically say that you can convert all these epsilons which are written in terms of some Q1, Q2, Q3 and Q4 in terms of something P1, P2, P3 and P4. For example, this one Q1, Q2, Q3, Q4 is nothing but epsilon P1, P2, P3, P4 using the same property. So then L mu is half 1 over epsilon P1, P2, P3, P4 with D0 epsilon mu P2, P3, P4 plus D1 epsilon mu P3, P4, P5 D2 epsilon mu P4, P5, P1. You can use the cyclicity and you would be able to write everything. You don't need to compute. D3 epsilon mu P5, P1, P2 plus D4 epsilon mu P1, P2, P3 and this term sorry, just to, I think I should correct a few things here. I forgot this epsilon here. This I have taken out as a definition of ui, so this goes only up to this. This is minus half because it's still ui I have, and this is also minus half. Please correct this and check also. I might still have some more mistakes there, but I have sum over I 1 to 4 qi squared and ui mu. Okay. See, this is an innocent term because it doesn't have any loop momentum. The things that we want to manage are with the loop momentum. Okay, so that is the expression that we are going to use. Okay, this is the expression which is going to help you reduce any 5-point tensor integral into a lower one. So let's just look at the one which can appear in this process. So that's your, say, E mu nu rho. That would be L mu L nu L rho divided by D0, D1, D2, D3 and D4. And what do I want to do? I want to basically just look at this L rho. I don't worry about this. Let's look at L rho and express that L rho. Use this expression here. Okay. And what are you going to see? So apart from this, when you write down this L rho, what is going to happen? With every term, you are losing actually one propagators. So here D0 is gone, only 4 are there. D1 is gone here, so D0, D2, D3, D4 is there, and so on. So these basically, all these terms, they can be expressed in terms of missing propagator notation. So, I write that as so let us take this term epsilon mu P2 P3 P4, okay, that is the term. And what am I going to get? I am going to get here D1, D2, D3, D4, but with 2 indices. So, it is a 4-point function with 2 indices, for which I can use the notation D, sorry, this should be rho, mu nu with this notation. So, D mu nu with the first this propagator missing, right, and of course, I have this guy outside. So, let me write that as well, 1 over twice epsilon P1, P2, P3, P4. So, P1, P2, P3, P4. Okay. So, I can basically write down the others also, which is nothing but now d mu nu with first propagator missing in this term, epsilon mu P3, P4, P5 plus d mu nu the second propagator missing, epsilon rho P4, P5, P1 plus d mu nu third one, epsilon rho and P5, P1, P2 plus d mu nu fourth propagator missing with epsilon rho P1, P2 and P3. Okay. This all actually comes from here, and this term is what? This term is completely there is no missing propagator. So, this basically gives a term with 5 propagator and 2 indices, which is, let me write down here, assuming that we are continuing. Oops. So, yeah, just a moment, I will write this term and then minus half sum over I qi squared ui rho times E mu nu. Yes.
Actually, I wanted to ask, like, out of these 5 momenta,
Yes.
4 of them are independent, only one is dependent in some sense. So, and you use that property in that relations also in the right hand side in the below relation.
Yeah.
But here in your answer, in this curly bracket,
Yeah.
you are introducing all 5.
All
like,
5. Yes.
So I am not getting why you are doing that. At the time there should be only 4.
Right. So, I am coming to that. I think that is an important point to address. But one of the reasons basically I use them, because my expression follows basically a very nice cyclic property, right? The way basically I have written down, one of the reasons basically I instead of basically just always working with P1, P2, P3, P4, one thing I can see that I can nicely see have say P2, P3, P4 here, then P3, P4, P5 there, and this cyclicity basically allow me to write it very compactly. Point number 1. Second, if I look at this one, okay, look at this term. In this term, the first the zeros propagator is gone. Therefore, what I am left with is D1, D2, D3, D4, right? This has L plus Q1, this has L plus Q2, L plus Q3, L plus Q4. And if I shift this, the Q1, okay, if I shift Q1, because this is a completely finite integral, if I shift that, what happens? I get here a term with corresponding D0. Here I will get basically a term which has L plus Q2 minus Q1, which is P1. Here I get L Q3 minus Q1, which is P1 plus P2. P2 plus P3, because I'm shifting L minus Q1, which is basically equal to P1. So here I get basically P2, here I get P2 plus P3, here I get P3 plus P4. So as far as this box topology is concerned, what is the relevant relevant momenta which are going in are P2, P3, P4. Similarly, if you move here, what you will find that when I remove the propagator, the D1 propagator, okay, when I remove the D1 propagator, I am left with D0, D2, D3 and D4, right? So here the momenta which are actually going are, now there is no shifting here, so P1 plus, P1 plus P2, then P1 plus P2 plus P3, and then P1 plus P2 plus P3 plus that's it, Q2, P1 plus P2, Q3 is there, P4, P4. Okay, that's what is happening. But what basically, so instead of, so you can actually work with this, it's not a problem. But since momentum conservation is there, okay, you can convert this set to basically this set, which says P3, P3 plus P4 and P3 plus P4 plus P5. Now P3 plus P4, P plus 5 is this, okay. P1, P3 plus P4, that would be, what is happening? Am I missing something? P3 plus P4 plus P5, P3.
One of them will not contain any momenta, only L square.
Which one? No, actually, I'm what I'm trying to say that what is the P5? P5 is okay. Okay, let me think about it. Maybe after I finish this, we basically fix this part. So right now, okay. So right now, basically, this is about right, because I'm using the momentum conservation. So I'm using the cyclic property and writing it basically compactly. Okay. But if you want, you can basically, if you don't want to basically do that, that is perfectly fine, because and at no stage I am going to basically lose the fact that one of these are dependent on the other. That basically I am not going to use, because otherwise we are going to basically face problem in calculating the gram determinant. Okay. Okay. So okay, let me come. So let's actually discuss this in a while. So what we have done here, all we have done, we had actually 3 rank 5-point function, which by using this expansion of L mu in terms of p's, you have been able to write them in terms of lower tensor structure. So for example, d mu news, but the d mu nu differs, like you will have basically 5 such possibilities, with missing this one or this one or this one or this one. These all 5 possibilities are represented here, and corresponding a 5-point function with 2 rank tensors. Okay. So the message here is that instead of writing down E mu nu rho as the most general decomposition and then evaluating the coefficient, that is not needed, simply because of this fact that L mu is completely fixed by the space of P1, P2, P3 and P4, and this is actually much more efficient, because as far as the recursive procedure is concerned. Okay. So now you can actually go on further. So this part we have already done, up to box we already done. Okay. So you adopt the process of reducing the boxes here the way you did earlier. Now what is left? E mu nu is left with the 2 loop momenta. You basically repeat that. What you are going to get? if you repeat that, you are going to get basically d mu, the expression in terms of d mu with one of these propagators missing, and e mu, right? For this, we already know what to do. We have done it basically in d dimension. You do it basically that. And for this part, what I do? Again, I go one step, and as you can clearly see, the only thing which I am going to come across here is basically d0 and e0, right? So nothing new from the point of view of going from higher rank tensor to lower rank tensor, because this we had seen in the case of 2 point, 3 point and 4 point. But what is new, that if you stick to the 4 dimension, which we can do for the case of 5 point functions, then you don't require that decomposition. Just use the fact that L is completely expressible in terms of P1, P2, P3 and P4, and this step is actually much more simpler as far as the recursive downgrading of tensor structure is concerned. Very quickly basically you reach at this stage. Okay. So this basically suggests that even if you have, say, now 6, 7, there is nothing new. All you have basically, you have got actually more momenta, but only in 4 dimension only 4 can be linearly independent. So you have got actually several choices to choose which 4 out of, say for example, if I go for a 2 to 4 process, I have got actually P1, P2, P3, P4 and P5. But in 4 dimension, only 4 can be 4 are needed. So you have this freedom to choose any 4 out of these actually 5 momenta. And from that point of view, there is no problem in reducing any 6 point tensor integral into lower point tensor integrals. So that way, at least what we agree, that any n point function, okay, it can be reduced into a scalar, okay, which has got basically n point scalar, n minus point scalar up to say 1 point scalar. Right. So is the question is basically, so I need to basically compute A0, B0, C0, D0, probably E0, corresponding F0 and so on. Okay. But this is where basically we again come across a simplification that in 4 dimensions E0 or F0 and so on, they are also not independent. They can be written down in terms of boxes. Okay. So we will do that actually now quickly, so that the claim that at one loop level in 4 dimension, any 1 point amplitude can be expressed in terms of 1 point function, 2 point function and 3 point function and 4 point function. That's all. Yes.
By epsilon yes. How do you simplify them further?
How do I
Simplify them further in terms of P1, P2, P3.
Oh, so I don't need to simplify, because what do I have? So suppose that I have it, right? Now in your amplitude, these all the loop momenta, they are contracted either with the some external momenta or the polarization. Okay. So these guys, they would always appear like say V1, V2, V3, V4, right? Where V1, V2, V3 is some vectors, and you have to basically in your program you have to compute them. That's it. You can, yeah, that would be you can use the determinant formula. Otherwise, basically you can directly using the property that epsilon 0, 1, 2, 3, 4. You can do that whichever way. But the point is that you are going to basically come across scalar objects, which the moment you tell what is your external momenta and polarization, your program can compute it. Okay. Yes.
L as a combination of metric tensor and momentum instead of
Is it possible to express
L mu as a combination of metric tensor and external momentum like P2, P3, P4?
What do you mean is it possible? I mean, it's not possible simply because metric tensor has 2 indices. That's why I would not like to do it. And the second point, that in this particular case, I mean the metric tensor is expanded in terms of external momenta.
Momentum with upper index and one is lower index.
So whatever you are saying, if you do that, it is effectively that equation that I wrote. The important, that's actually the most important point, that L mu is expressible in terms of P1, P2, P3, P4. Now whatever you do, you will see basically you will always fall to this. Okay. Is this fine? Any other question before we proceed for E0? Okay. So this would be, yeah, as far as the derivations are concerned, this is the last part of the derivation. After that, I'll have just a brief discussion on the merits or demerits of the reduction process. So what I want to basically show you that E0 is expressible in terms of D zeros. Okay, and again, what helps us is the expression of L mu in terms of Pi's or corresponding Qi's. So 1 to 4 L dot Qi Ui alpha. That's basically the starting point. And what I do, I compute L squared, and that L squared is I L dot Qi L dot Ui. So I multiplied with L alpha both the sides. On the left hand side, this is nothing but D0 plus m squared, and on the right hand side, this is half L dot Ui di minus D0 minus Qi squared, as we have done multiple times. Okay. Okay. So with this relation, what I want to do now, I actually multiply both the sides by or divide by all the propagators d0, d1, d2, d4, and integrate over d4l. Okay. So that integration we will not write. We will just actually write this part with the understanding that is always integrated out. Okay. So this term, the first term, is basically your d with the missing propagator 0. So this is d0 with missing propagator d0 plus m squared E0, the object in which we are interested in. Okay, so that's E0 has appeared here. And what we are hoping that on the right hand side, and I would be having scalars, not tensors. Okay, so that I show that E0 is written in terms of D zeros. Okay. So maybe here. So let's look at. So there are several terms. Let's look at this term, which is what? L dot Ui di over d0, d1, d2, d3, and d4. I have got 4 terms here: L dot u1, then corresponding d, L dot u2, and so on. So that's the general term. Let me actually write down just for the first term and then argue what is going to happen. Now, because of this, d1, this will cancel, and what I have got? d0, d2, d3, d4. What are the momenta here? The momenta are q2, q3, and q4, right? q2, q3, and q4. And here basically, so I have got one rank 4-point tensor integral, where the relevant momenta are q2, q3, q4. So when I expand it, it would be expanded in terms of q2, q3, and q4. But that q2, q3, q4 would hit u1 and from the property of ui dot qj equals delta ij, that term would be 0, right? And you can imagine the same thing is going to happen with the second term. When there is a d2, you will have u2 sitting here. The d2 is going to kill q2, and the relevant momenta there would become q1, q3, and q4. Again, it's a one rank tensor which would be expanded in terms of q1, q3, and q4 only. So again it is 0. So this term is actually 0, right? This was basically the term which would have given us basically tensor integral, but that's gone. The di part, that's gone. We all agree with this? So let's now look at basically this term, the second term, d0 term. So the d0 term gives me here sum over L dot ui with I multiplied with d0, but that is actually d1, d2, d3, d4. So with the d0 term, I remove this d0, I got d1, d2, d3, d4, and here this is sum over L dot ui. Now, but what is this? This is actually L is outside, I can take, and this is sum of ui over I from 1 to 4. I gave you an exercise a while ago that sum over I of ui is equal to v1. So if you do that, this is basically L dot v1 divided by d1, d2, d3, and d4. Okay. Now this has q1, q2, q3, q4, right? This has L dot v1. So what I'm going to do, I will basically shift the loop momenta L to L minus q1 to put basically this in the standard form. And when I do that, what I'm going to get it here? I'm going to get here L dot v1 minus q1 dot v1. Is this fine? L dot v1 becomes L dot v1 and q1 dot v1. Now this L dot v1 has a propagator where the relevant momenta are p2, p3, and p4 after shifting. So this again, when you expand, the momenta which will appear here, they would be p2, p3, and p4.
I couldn't follow you.
This step?
No. Even after.
After summation, yeah. So let me write it down. So this step is, I put basically L alpha right hand side, take it out, right, and the sum over I ui alpha, right? And this, I gave you an exercise, I didn't do it, but we can do it in the tutorial. This is nothing but v1 alpha. That's the exercise. So therefore this is L dot v1. Now this L dot v1, because d0 has gone, the leftover propagators are d1, d2, d3, d4, and here, to put it basically in the standard form, I am going to basically shift the loop momenta by L minus q1, which appears here. So the propagators, they become something like this, say d0, d1 prime, d2 prime, and d3 prime, where d0 has come from here because this was L plus q1, so that became actually L squared. This was L plus q2. Now after shifting, this has gone into L plus q2 minus q1. This has gone to L plus q2, q3 minus q1, and this is q4 minus q1. But after you remove p1, the momenta which are relevant are p2, p3, and p4. p1 is out of picture. And if only P2, P3, P4 are relevant, then if you look at the first term, which is L dot V1 divided by these 4 propagators, this is a 1 rank 4-point function, which would be expanded in terms of P2, P3 and P4. And those P2, P3 and P4, they would be dotted with V1, which by definition of Vi dot Pj equals delta Ij would also be 0. Is this okay? So, you have to use the property of these objects for simplification. You can do it actually brute force way also, but since we have introduced these objects, it's good to utilize these properties. Okay. So, we are almost done. The good thing is that we have got rid of all the L's from the numerator, and as you have seen from that actually appeared here, that appeared here, okay, and there's one more term which is left. Where is that? Which one? Qi squared. Okay, so Qi squared. Okay. I don't see it basically in my notes. Where are they? Have I written it correctly? L dot Ui. Yeah, let me just quickly spot that, because otherwise we will be having this term. So 2m squared d0 is here. Okay, yeah, so I have spotted that. Let me write it. So sum over I L dot Ui times Qi squared. This I am going to basically write as L dot sum over I Ui Qi squared, or let's say alpha and alpha. Okay, and so this is a vector. I denote this vector, which doesn't depend upon loop momentum, as W alpha. Okay, so we have this, and now, so the last step would be to deal with L dot W over D0, D1, D2, D3 and D4. Okay. So, we have taken, this is the last step, because Di has been taken care, D0 has been taken care. The left hand side is super clear what it is in terms of a scalar. So, let us just look at quickly L dot W. So, L dot W alpha, this is L alpha and W, and I am going to basically use another time the definition of L in terms of this definition. So, that gives me sum over I L dot Qi Ui alpha and that W alpha. Okay. So, this part again can be written as Di minus D0 minus Qi squared with Ui dot W. Okay. And I am going to get from here So this is basically again in terms of missing propagator notation, this will be from here I will get D0 with missing I. From here I will get D0 with missing 0, and from here I will get E0. Can you see this? So I had this term left, 5 propagators, using again L alpha in terms of this L dot Qi and Ui. I basically come across this decomposition, and in this decomposition, since I have got these 5 propagators, I am going to basically get 4 here with one of them missing, 4 here with 0 of them missing, and E0 here. Okay. So I have got rid of all L's in the numerator, and as you can see, what we have got actually 2 kinds of stuff: E0, the 5-point scalar, and D0s which arise out of removing any of the propagator of the 5-point function or the reduced scalars. So you can clearly see that E0 has been expressed in terms of D0s.
Problem here itself got reduced into box.
Yes, exactly, and that was the claim, that the 5-point function, the scalar function, it can be written in terms of 5 boxes which arise from which can arise from the box by removing one of these propagators. So 0, 1, 2, 3, and 4. So there is no point in writing the complete expression. I mean, we can. I am going to basically share with you the references anyway for all the lectures that I have given. But I think what I certainly want to write is this, and where we need to agree, because this is what we have done, and we should be basically able to say that yes, we agree with this statement in 4 dimensions.
One naive question.
Yes.
Actually, we can, let's say for a moment, we can agree on that the 5-point function can be reduced into 4-point function. But the thing is, sir, I can agree intuitively because there is in 5-point function 5 momentas are there, and I can say that okay, one of them has to be dependent and 4 of them can be independent, and so hence I will say that it can be reduced into 4-point function.
Okay.
But what about the 6-point or higher? Because there you will have in the 6-point function there you will have 5 momenta independent,
right,
and 1 dependent.
Okay.
So that can be done. I mean, then I cannot give this logic that what I am giving right now.
So let's actually address that. But before addressing it up to 5-point, do you think like we are? I mean, have I convinced you that we can do this? Do you agree that at least up to 5-point function, the thing to worry about are scalar integrals up to 4-point function only in 4 dimensions?
Whether they are massless or massive.
Yeah, that is independent of the internal line and external line virtuality and so on. Okay. So if we agree with that, then let's ask the question that he asked. Suppose that I am looking at 2 to 4 processes. Okay, 2 to 4 processes in 4 dimensions. I have got actually 5 4 and 5, and the 6th one is basically determined from the momentum conservation. This is what I have got, right? In 4 dimension, I can have actually maximum 4, but I have basically access to 5. All it says that you have a choice now. Something which was actually unique at the level of 5-point function in terms of P1, P2, P3 and P4, you have basically choice. And the choice is basically choose 4 out of these 5 and express your loop momentum in terms of that. If you can do that, then whatever has been done for the pentagon, it has to basically follow for the hexa, for the hepta, or for any endpoint function.
So
So all I'm saying basically that up to 5-point function, we had got actually 4 independent momenta, and we said basically I would uniquely express my loop momenta in terms of those 4. But when I'm discussing say 2 to 4 scattering or 2 to 5 and so on, this set is actually increasing, but I'm still in 4 dimensions. What I need actually 4 independent vectors. Okay, so I have actually choices. That's all. So you choose, and it has to follow from the same argument that we have given here for the tensor, higher tensor to lower tensor, and then from tensor to scalars. This has simplified your job enormously beyond 4-point function. It's all about repeated use of this. Every time it gives you basically L dot Q, and therefore differences of propagators. Therefore, you are bound to basically get lower point tensor integrals as well as ultimately ending up to the scalar integrals.
So that means if we start with the first we will go to 5 point. After that, this 5-point function, which will 1 momenta and go to 4.
Can you please repeat that again?
Like for example, let's say we start with XR. I mean 6 points.
Suppose we have 2 to 4 process. Yes.
Yes. So we have 5 independent momenta.
Yes.
So from there we have to reduce everything in terms of 5-point functions. While this 5 independent momenta will appear. Now in this case we can choose 1 momenta to be dependent because these all are pentagons. Now from there we can use this process recursively to go to 4 points.
So I partly agree with you. See, the process
The
is
momentum
recursive.
conservation argument we will not be able to use now.
So the process is recursive. Suppose that you go to the single phase, no? Right? Now we can actually nicely see that what I'm going to come across is say something like this. Okay, I've got 4 propagators, something like this. Okay, the first step is always to go from here to this. It's a recursive process. This is what I have explained. Now the question is, in the case of hexa, how do you do it? Okay, and the answer to that is basically that you still use that L mu. Okay, but which choices to actually make here? And this is where probably you have to take a call. Maybe some nice combination basically would you help you reach faster or slower, but that you have actually choices to make if you want to express L, because 4 only are independent. So you make that choice, okay, and you continue with this. Now you will at some stage you will reach at say F0 and E's, which will depend upon that 4 momenta which you had started, okay, and therefore the process basically continues. Okay. So with the reduction, because you are removing a propagator, you would always know what is the set that is available to you. You use that set. If you are still up to a 5-point function, that set basically would be unique for you to express L. If you are at higher point function, then no, there are actually other possibilities. For example, I go from 2 to say hepta, okay, from there to there. So this there are actually many choices. You have to make a choice up when you reach at 5. Naturally, basically that gets fixed uniquely as far as expressing L in terms of external momenta is concerned. Okay. So I hope you have this picture where effectively what happens if you look at, say, for example, penta. I mean, I think it's good to visualize them. So if 1, 2, 3, 4 and 5, and then when you say basically it is going to get reduced in terms of 4-point functions, what is effectively happening? You are basically going to come across something like this, right? 1, 2, 3 plus 4 and 5. That's what effectively happens. That's the missing propagator. So what is flowing in here now is P3 plus P4, right? And this way, something basically which was, for example, suppose that all of these were massless here, when basically this guy enters, P3 plus P4 squared is no more actually 0. So that basically gives you a situation of 4-point function where 3 are massless, 1 is massive. Okay. So what you need to do, although it is true that you have to basically only worry about 1-point function, 2-point function, 3-point and 4-point function, you should basically now classify all the cases depending upon whether all my external momenta are actually massless, some of them are massless. So you classify. Once you do this classification, you can solve these these integrals, these scalar integrals, and this way you reach a finite set of basis integrals in 4 dimensions. Okay, often basically they are called master integrals because you have to evaluate them once and for all. You prepare your library of these. Now, depending upon the process, you will always know that which situation I have fallen into. You just basically, your library will tell you use that situation, and therefore that particular evaluation of a scalar integral would be used in my calculation. Is this clear? Okay. So shall I actually take 10 minutes just to say to make a small point here? Okay. Okay, so we have convinced ourselves about the reduction of one loop amplitudes. Any one loop amplitude, it depends on finite set of master integrals which are identified as 2-point, 3-point, 4-point and 5-point. What is sitting in front of them is the process dependent part. Okay, and this is what basically we need to this is what we get actually when you describe a specific process. A0, B0 you have calculated once and for all the processes. Okay. Now the question is, in this reduction procedure you have seen that when I move from say a higher point function, say C mu nu, to a lower point function, I am taking the example of 2-point function, what we had come across, this process introduces a chronicle delta in the denominator. Do you remember this? While doing the tensor reduction, we came across actually this object. When I basically go to C0, I again basically introduce another chronicle delta. So in 3-point reduction, the chronicle delta, which is a determinant, it depends on P1 and P2. So this is P1 squared, P2 squared minus P1 dot P2 whole squared. Suppose that you have a 3-point function, say box. When you do the box, you will have corresponding chronicle delta, which is P1, P2 and P3, the determinant of that, you compute that. Okay. But sorry, no, not 4, it's just this. Okay, this guy, remember that we had written it as delta P1 P2, P1 P2, and then it has that determinant structure. So this reduction, when you reduce basically every tensor rank, you introduce 1 over delta in the corresponding reduction. If you are doing 4-point function reduction, say 4 rank to 3 rank, you are going to introduce 1 over delta 3. Then 3 to 2, 1 over delta 3 again. So somewhere you are going to get 1 over delta 3 squared, delta 3 cube and 4 and so on. Okay. Now the whole reduction, it relied on a crucial statement that P1 and P2, and for that matter P1 and P2 and P3, they are linearly independent. Okay, independent versus actually linearly independent. What does actually linear independent means? Of course, whether I can basically express this in terms of this. If I can express P1 in terms of P2, then I don't have linear independence. So certainly you cannot basically apply any of this to a problem where P1 and P2 are linearly dependent. Why? Because the gram determinant, this would vanish, and it is sitting actually in the denominator. Since you have done the analysis assuming P1 and P2 are linearly independent, you should never basically apply that to a problem where they are linearly dependent. Makes sense. Everyone basically would agree with that, and would you would like to ask also, okay, fine, but why that is important? Because I know that P1 and P2 should not, if they are linearly dependent, I will not use it. I am actually wise enough. So where is the problem? Why actually we are talking about it? We are talking about it where these objects are used. Whatever the calculation we have done, they are to be basically computed for a scattering process, right? And when I say basically I am going to measure this process, such a process, and compare with an experiment, I have to tell actually what is P1, what is P2, what is P3, what is P4, and so on, right? Because that's what actually you measure. You measure basically when you perform the experiment, you prepare the beam in certain momentum states. You know what is actually P1 and P2, and then after performing the experiment, you look into the detector and you identify the particle. And identification means knowing what is P3, P4, P5, and everything. That's what basically it means. So the question is, in all those events where like P1 and P2 going to P3, P4, and P5, are they basically always linearly independent? That is the question. Okay. The only thing that is crucial in scattering processes is this: sum over Pi is equal to 0, assuming that all of them are incoming or outgoing, or P1 plus P2 is equal to P3 plus P4 and 5. That's the only constraint, that's the only condition. So when you simulate the environment of an experiment, you generate the phase space for the final state particle given the input energy. And in doing that, you only worry about this, that whenever basically I do P1 plus P2 and generate P3 P4, I would ensure that P1 plus P2 is equal to P3 plus P4. That's the only constraint you do. So there is no guarantee that you would not basically come across a phase space point, meaning P1, P2, P3, and P4, where two of them are actually not linearly dependent. In phase space generation, that is not a requirement. Okay. So that's the reason why we need to actually worry about this part. If my phase space also had taken care of that, then I would never worry about it, because I have a very good scheme. It tells me if things are linearly independent, I'll just actually supply all the information, we'll get a number. But anyway, even suppose that I got actually linearly dependent situation, I came across that in certain events, I'm actually wise enough not to use this one and use basically the set which is indeed linearly dependent. We can do that. Instead of, say, for example, P1 and P2, if they are linearly dependent, I'll say basically now I work with where P1 is only dependent. So that would be a separate scheme. You can do that. The problem is not choosing whether to work with P1 and P2 or to work with P1 or P2, depending on the situation. The problem is that when you do these computations are done numerically. Okay, and the point to worry about is not linear dependence, exact linear dependence, but near linear dependence. And by that I mean, so in this case, suppose that I have P2 equals x P1 where x is not 0. Okay, that's what basically linear dependence, simple minded definition of linear dependence would be. But this is exact situation. I know basically how to handle it. What I don't know basically how to handle it, especially numerically, is that if I have a component such that P1 dot delta is equal to 0, which is a measure of loss of linear dependence. If this is 0, then it's completely linearly dependent. If it is non-zero, in a strict sense, they are actually linearly independent. So analytically no problem, but numerically there is a problem, that what this is. Because when you do the numerical computation, you work in a finite precision. You work in a finite precision. In a single precision, the 0 is not 0. 0 is like 10 to the power minus 8. That's the definition of 0. In double precision, it is 10 to the power minus 16, which is 0. Okay? So finite precision, you basically, your definition of 0 changes. Let's see what is the consequence of this. This is a small orthogonal part that I have introduced to describe the situation of near linear independence. So delta 2, so with this, P2 square would be what? P2 square would be x squared P1 squared plus delta this, and the dot product would be 0. And what is P1 dot P2? P1 dot P2 would be simply x P1 squared. This is fine, right? Because P1 dot delta perpendicular is 0. Therefore, my Gram determinant is just basically a naive way of telling you the problem which one would come across while computing the matrix element numerically. So this would be your P1 squared P2 squared, which is P1 squared x squared P1 squared plus delta perpendicular square minus P1 dot P2 whole squared, which is x squared P1 squared whole squared. Okay, and I get rid of actually this term, and what I have is P1 squared delta perpendicular square, which goes as this. Okay, so that's how your chronicle delta would depend on this regulator or measure. Okay, so suppose that I just imagine C mu nu rho to C mu nu to C mu to C0. At this step, I have introduced actually one chronicle delta, therefore 1 over delta perpendicular squared. At this stage, another 1 over delta perpendicular squared whole squared. At this stage, another chronicle delta, and therefore 1 over delta perpendicular squared to the power 4. Right? Or naively, 1 over delta perpendicular to the power 6. Okay? Now let's say in the single precision, I have, say, suppose this actually 10 to the power minus 4. This is not 0. Okay, in single precision this is not 0, this is 10 to the power minus 4. The kind of actually number you are going to generate here is 1 over 10 to the power minus 24, which is going to basically give a large contribution to the numerator. Okay. Oh, sorry. 2, 4. So 2, every time basically I get delta square. So what is 4? And what it should be? 3. Okay. So this would be, so this is fine. Is this fine? 6 is fine. Okay. So yeah, so just wanted to emphasize that you see, you are going to basically generate a very large number, and this is a situation which exactly, truly speaking, analytically, it is not actually linearly dependent, as long as this is not strictly 0. But this is where your numerical computations, when you do the numerical computation, you have to give meaning to what is 0, what is small, what is large. So even if you don't want, you will come across a situation where you will be using these expressions, okay, for tensor reduction to the scalar and therefore the evaluation of the matrix element, and you would hit a phase space point where there is a near loss of linear independence, and you will come across large numbers in your expressions, and this basically gives rise to numerical instability in your calculations.
This is a specific phase space problem, but otherwise at the amplitude level this should not happen.
Yes. Yeah, it's basically I mean, what we are trying to say basically your amplitude is finite. Okay.
I mean, while working on an amplitude, we simply take
one amplitude as independent. We don't care about the near dependence, near loss of linear independence, unless we are talking about the phase space level.
But this is a practical situation. Whatever you have to generate a phase space, and one of the phase space basically would be of this sort. So it is there. Now the question is whether you see or not. It depends upon with what precision you are working in. And if you come across such a situation, one naive way basically or simple minded way would be to see whether you can increase your precision, and this problem actually is not is handled within the machine precision. Okay, or you basically take some alternative methods. So for example, you say whenever I come across this situation, I'll basically have a different expression or a modified expression for my reduced amplitude, which would behave nicer in such a situation. And that's what actually people do. That's what, when they build basically a tool for the automated computations of loop amplitudes, they do worry about such phase space configurations, and therefore they use methods where such problems are not faced very often, okay, or a method which is completely independent. For example, what Satyajit talked about, he talked about basically this cut based method. For example, one of the popular program OPP method, which is a numerical way of computing it, it doesn't actually rely, it doesn't basically directly seize the Gram determinant, okay, although they are actually present even in the scalar integrals. But as far as the procedure, since you have seen this procedure, they don't basically see the Gram determinants typically. That's actually more like algebraic manipulation than basically a reduction. Okay, so that is handled separately. Yes.
This kind of diode will appear in amplitude also, because we are factorizing the amplitude in C0, C1, and this delta 1 part will appear also as a coefficient of this scalar integral. So it's not only in the phase space but also in the amplitude part, if we calculate only the amplitude.
That's what I actually said, no? I already mentioned actually where they are appearing. They are appearing in the process of tensor integral. I'm trying to tell you the source in your program in the phase space.
And the problem in the phase space also enters in.
It's not actually a problem in the phase space. The source in the phase space, basically such configurations are bound to be generated. Once basically this phase space is generated, you have to feed this in your amplitude for the evaluation. And the moment you do that, you come across this situation. Yes.
Sir, but Gram determinant also has dependence on P1 square.
Yes.
How about that brings about the finiteness?
So yeah, as I told you, basically one of the things that you have to also worry about, depending upon external virtualities, you see whether your reduction is valid or not. This I basically showed you in the case of 2-point function. Whether p squared is 0 or not, the reduced expression of tensor integral in terms of a scalar is different. So you have to worry about it. So you clearly state always, like in mathematics, you state that what is the assumption with which you begin. After that, if that actually covers a situation of say p1 square is equal to 0 and all that, you are in, you can say basically yes, it's very good, you are happy with that. But you should not expect that would actually work for that situation, which you never basically started, which you never started with. Okay. Yes.
How are similar problems handled for multiple amplitudes? Because there we don't have a very straightforward approach of constructing these coefficients. So we typically employ projectors. And how do projectors that we construct manually capture the information of such problems? That you are talking about linear, almost linear loss of decay.
Right. So I don't have actually much experience in the multi-loop, but what I can actually say just from the experience that we have, if you are coming across this problem in one loop, of course, as you said, basically you expect to face them at multi-loop as well. And I believe since we know what are the possibilities, for example, just without basically changing the method itself, there are ways to handle them. And I said one way to handle them is to, say for example, increase your precision, machine precision. So that would be a simple-minded way, even if you are coming across such a numerical instability in, say, multi-loop. However, the problem basically with this is that your computation becomes extremely slow. You cannot basically afford to do all the computation in, say, quadruple precision or higher precision. But then you will, since you know what is the source or what is happening, if you can identify, then you can say, okay, for all the regular phase space point, I am going to basically use this path where I know that there will be no problem. But whenever basically I hit such a situation, I would have a way to identify that I have reached that situation before the computation, and then I do something. Either basically I just evaluate that phase space point in quadrupole and higher precision, or only for those phase space point I use a modified expression. This I believe that is a general thing to do even in multi-loop cases, although I myself have not come across, because I haven't basically got into the numerical evaluation of two loop amplitudes myself. I mean, there are codes which do it, and as you said, I understand that they have done something in those codes like PySecDec or what is that code, this AMFlow. They are purely numerical, and I'm sure basically they have things implemented which take care of this.
Sir, is these large numbers are at the amplitude intermediate level, or finally when we do the complete reduction of the amplitude, the large number becomes cancel out and gives us small number?
So see, they are distributed. As you can imagine, they are distributed, and they are distributed in terms of, say, if in a 2 to 2 case, they are distributed in terms of like delta 3 and delta 2. Okay. So, as he was probably trying to say that if you look at the amplitude should basically be well behaved, right? But you have done basically a process where now you come across such a situation, okay? So, it is actually so this is what happens, different parts, they give basically, so suppose that I got a basically large contribution. When you increase the precision, what happens, that large contribution from one place, and there is a cancellation among different pieces, and they are well taken care with increased precision. Okay, that's what effectively happens. Yeah. So they are there, but they will be, because the precision is high, you know basically how to basically subtract two large numbers. That's the idea. Okay, any other question or comment? Yes.
So I have a question, like we said like theta equals linear dependent from the perpendicular to E1.
Yeah.
So it's like, can we bring about the conservation of momentum, like to bring about a constraint on delta, like there must be a lower limit beyond which we cannot take that.
Probably. But what you said basically, I mean, this thing is conservation of momentum. Again, when you are doing things numerically, then P1, so sum over Pi is equal to 0. In a computer code, the right hand side is not 0, right? So what you are saying basically that this is, say, single precision, it is 10 to the minus 6, 10 to the minus 8, and you are happy with that, right? You cannot basically in single precision generate a phase space where you expect to get this sum over Pi is equal to 10 to the minus 16. Okay. So the problem begins actually from there itself. It's about basically doing the computation with finite precision. If you can do computation with infinite precision, I have an impression that you are in good shape, but it requires actually a lot of resources. Computer, you know what I mean? You have to feed a lot of electricity so that one single point it computes in 1 hour or 2 hour or 2 day, whatever.
Why can't symbolic computation like delta 1 keep it symbolic and finally it should like cancel in such a way that the amplitude is well behaved?
Right. So this is an important point, and I don't think it requires much explanation. When people spend a lot of time, even using this method, to obtain a very compact expression of the amplitude. See, this is a process of reduction, right? But then now you have got everything, right? A0, B0, C0, D0. So what people used to do, and they basically still in some cases they do, they try to basically simplify as much as possible, getting less and less prone to this kind of a issue. And indeed, people have spent actually time in getting compact expressions. The problem is, again, as I said, if you algorithmically do it, it's very convenient, but then you are actually bound to face such a situation. So, and people develop basically numerical techniques so that it is actually faster, it is automated, it doesn't actually require like when experimentalist colleagues are performing experiment, right, they have several processes to look at, okay, and ideally basically they would need for comparison, say for example with the standard model prediction, some code so that they can simulate and compare with the data. And there are two possibilities that you, for example, for every process you supply that code and make sure that basically it is less affected by numerical instabilities, and then they use it. But then tomorrow basically they say that we need this process also, then somebody has to again work and do all these things. And somebody thought about basically automating things so that they don't actually every time they have to wait that whether this is available or not, you generate it. So in this automation you have to basically do certain compromises. This is what basically my impression is. Otherwise to a very good extent you can take care of such an issue by obtaining a very compact expression of amplitudes by doing a lot of simplifications, and people have done it. People here, your supervisors, they have done.
When you mean compact expressions, you mean compact numerical or compact analytical?
Compact analytical expressions, because he was saying basically that you have these deltas here and there, but what about when I combine everything, okay, write down the, not say for example in terms of A0, B0, C0, what I know that this A0 they have B0 they have some logs, C0 they have got some dialogues and so on, and these are special functions. You put those things and analytically basically try to simplify so that now all your expressions are written in terms of logs, dialogues and some rational functions, and probably that expression is so compact it has got rid of a lot of this. So if delta can appear here, some factor basically like delta can appear in the numerator also in this process. So probably this naive thing is not this you can say this is something worse situation, but when you have compactified the situation, it is say probably 1 over delta square only. Isn't it better? What basically doesn't work in say double precision here, if it is just delta square, that would be 10 to the power minus 8, it would be very well taken care by the double precision computation of that expression. That's what I mean. Okay, shall we stop here? Okay, thanks.